Hi again. We're continuing our exploration of sampling distributions of a mean. And I have the previous notes page, partly because there's a note at the bottom about what we're going to do next. But I also, after the last video, I was fixing my wording on the bottom of the graph, and I remembered that it's really useful to put the sample size in the label of your graph. So notice how the sample size completely changed the graph, right? It changed the standard error, it changed the shape, it changed the spread of the graph. So for the first one, I went ahead and wrote average salary, and then I inserted average salary of 10 baseball players in millions. Or it could be random samples of 10. So another way I did it a different way in this second one, average salary in millions for random samples of 50 baseball players. So either way, however you want to write it, average is important because that's what we're calculating. We've got the units, and then random samples, and then the size, because that's just really going to help you remember what we're doing and keep it more concrete, okay? And then, of course, if you're communicating to someone else, it helps them understand as well. Okay, so we started with a population that was really skewed to the right, correct? We had a few baseball players making a lot of money, making more than everybody else, right? Okay, so what about other population shapes? Okay, so there's a better app to explore this with. It's in the online stat book link. So the link is here and it's right above this video. And I also have a page that has all of the links that we're using by module, because I know there's a lot. But different ones are good for different things. So I want to show you this online stat book sampling distribution mean applet. So I'm going to go over there. What we're going to do is choose the parent population shape. Sometimes the population is called the parent population. Then we're going to select mean, because we are studying means here. And then we're going to compare size n equals 5 and n equals 25. Okay. And then, oh, they have a 10,000 button, so they don't have a 2,000 button. Let's go over there and I'll show you. And when you click on the link, you get this instruction page to start with. So the begin button is in the upper left. So go ahead and click on the begin button. Of course, you're welcome to read any of the instructions that you like. And that shows 1, 2, 3, 4 graphs. And right now, the default is a normal distribution. So in the very upper graph, I can see my choices are normal, uniform, skewed, and custom. Okay, so I'm going to keep it on normal because our first one was skewed. We saw what happened with that. And this one I like because it has an animated sample. So let me just make sure we want mean equals 5. And then we also want mean, and we want the biggest this one will do is 25. Okay, so this second graph down will be the random sample of size 5. Then we'll have the mean of that, and then we'll also have one of 25. Okay, so I'm going to go ahead and do animated. You can see that 5 blocks fell down. So those were a random sample of 5. And now it's also doing a random sample of 25. If you prefer, you could just do the 5 at once. Let me do that again. So it's going to choose 5, and then it puts the average down below. And this is great because you can see how, because it's a random sample, you're getting a sample throughout the distribution, right? So here you can see the sample of 25. And you're getting some lower, some higher, and a bunch in the middle, because this is pretty symmetric, right? So it seems to make sense that this would be symmetric. So now you can do 5 if you want. It won't animate it. Or you can just go ahead and do 10,000. Okay, look what happened. So I really like this particular app because you can see the means in red. So look how the mean has not changed. And that makes sense. If you're taking a random sample, the mean of the random sample should be around the mean of the original population. But the spread is what's changing a lot. And this is what we can see really nicely on this graph, is that while the shape, they're still both symmetric. So once you're symmetric, you're always going to be symmetric. But this, what we call the standard error, is actually getting quite smaller, right? So we had a population standard deviation of 5, and we don't really have a context for this one. The standard error for a sample size of 5 is 2.25, and the standard error for a sample size of 25 is 1.03. And you can just see visually that the distribution is getting narrower, but it has the same shape. Okay, so interesting, right? Let's just do skewed to the right because we've already seen that, but I want to just see it with this scale. So if you'd like, you're welcome to do a couple animated. It's kind of fun. We can see because it's skewed to the right, more of the values are coming in from the left. And it kind of, our sample kind of fits that shape, right? As it should. So do as many animated ones as you want, or the 25 takes a little bit longer. The 5, you could do a few 5s if you want, or just go up to 10,000. Okay, so this is kind of what we were seeing before, but notice how with sample size of 5, it's actually already pretty close to symmetric. So that tells me this one is not as skewed as the baseball player salary one, and this is going from 0 to 32, so it is definitely less skewed than the other one. And then at 25, it looks really symmetric. Okay, so that's what we're going for. And again, standard error getting smaller, but the mean staying the same. Here, the mean is the red one, and the, actually, sorry, the, oh, it looks like it's blue, but it's, the mean is blue, but the blue and the red are overlapping because they're really symmetric. Okay, well, this can't work for every shape, can it? Let's try a uniform. Uniform is when each bar is approximately the same height. And let's try a couple animated. So it should be just coming from anywhere in this rectangle, right? Okay, I'll do a few more, and I'll do 10,000. Wow, that's so interesting that even though we started with this rectangle with this straight across uniform shape, when we take the averages, we still get a unimodal symmetric distribution. And this uniform was already symmetric, so it wasn't skewed, but it had a different shape. So isn't that really interesting? So n equals 5, we have a symmetric distribution. N equals 25, it's also symmetric. And our center is staying the same, right? The mean and median are about the same because it's symmetric. The mean is staying the same, but again, the standard error is getting smaller. So from 9.52 to 4.26 to 1.92. Okay, now you ready for the really even more fun part? You can do custom. So if you drag your mouse, so hold your mouse button down and drag, you can make your own population. So I'm going to make kind of a, almost like an inverse, it's called a bathtub curve. So it kind of looks like a bathtub where it goes down and then it goes back up at the end. Or you can make it more jagged, like look like a cityscape. Play around, make whatever you want, okay? And then I'll probably just skip to the 10,000 right now, but you're welcome to animate it if you want. Look at that, still symmetric. Well, my parent was fairly symmetric, not exactly. My left side had a little more frequency than my right side. Still coming out normal, and the center is staying the same. Let me try, if I do clear lower 3, let me try another custom. Oh, I've forgotten how to erase the custom, but I can just kind of go over it. Let me make more like city, like that. Okay, so I challenge you to find one that does not come out symmetric, okay? Isn't this interesting? So On the next notes page, I have a printout for you that summarizes this. So let me go over there. So I have all the different shapes. So we have, if we're starting with a normal, it's always normal. Oh, the other thing you can do is fit a little normal curve over it. Let me go back. If you click these check boxes, fit normal, it'll show you, we'll study a normal distribution, but this shape just comes up naturally, which we call a normal distribution. So you can see that it roughly fits that shape. So that's why I said if we're starting with a normal population, then it's always normal. If we're starting with a different shape, if it's symmetric, it's pretty much always symmetric, right? But if we start skewed, then we need, the more skewed it is, the higher sample size we need to get to a symmetric distribution. And here's one of my custom ones right here, okay? So we'll summarize this in the next video, but I don't know if you realize how revolutionary this is. Like, what this means is we don't need to know the shape of the population. Isn't this brilliant? Because we don't often know, okay? We might know some things tend to be normally distributed, so we may have an idea, but this is called the central limit theorem. It doesn't matter the shape of the population. When we look at the distribution of random samples, we will always, as long as it's big enough, as long as our sample size is big enough, we will always end up with a normal distribution. So this helps us in the theory. So when we get to the theoretical part of the central limit theorem, this really helps us with the theory. And then when we're doing simulations, we will also just see that this is usually the shape we get. Okay, thanks for watching this, and keep playing around with it, and I will summarize in the next video. Okay, see you there.